the formula. Now it's just a matter of, can you go and sit with some problems, right? Take the derivative, square it, put it into that formula, see if you can evaluate the integrals. Now, in the notes, I continue to give you more, right? In the notes, if you go back to that picture, do you see in the top, it says, if y is a function of x, here's your formula, right? But what if x is a function of y? What if it's the other way around, right? What if x is a function of y instead? Well, we should still be able to find the length, right? I mean, it should. And the formula just changes ever so slightly. Instead of going from a to b, we go from c to d, the limits on our y. And then our formula is still the same, but instead of f prime of x here squared, it's g prime of y squared. Seem reasonable that that should be very similar to the formula we just had? It's because we would draw the same picture. You know how I drew that right triangle and did Pythagorean? We'd be doing the exact same thing. So that's why the formula is going to look almost identical. I'm not going to test you on that second one. In your notes, I want you to have it, that's all. Okay, we move on. We're done with that section. We're moving on. So now what we're going to do is we're going to change our focus again to a different problem. That was arc length. For this next concept, we're going to go back to this idea of having a function again, right? This is, yeah, I think that's as big as I'm going to be able to get it. Y'all see that curve there? Yeah, you can see that. So in two-dimensional space, sorry, it's a little tilted, but that's our standard function on a flat sheet of paper, right? Now, we have revolved that around the x-axis before, haven't we? And we found the volume of the solid. So what we did before, what I'm about to show you, is we said, if you were to take the area, right, from here down, take that area, that whole region, and wrap the region around, you get a solid, don't you? Or sometimes we got washers, and right, and then you get like a solid with some hole in it. But this is a different question. What we want to do now is we want to wrap it around the x-axis, right? But just the curve, not the whole region below it, just the curve. And if you, ooh, whoa, what happened? There it is. If you wrap this thing around the x-axis, that was unimpressive. Let's turn it to the side. There we go. So if you wrap this thing around the x-axis, right, but just the curve itself, you no longer have a solid, do you? You have this, I don't want to say shell because I don't want to confuse it with Shell's method, but you've got this surface, don't you? It's just a surface. And so the question is, what is this surface's area, right? What's the area of that? So there's a difference, right? Volume was like how much stuff was inside this solid, and area would be, if you were to paint it, right, how much area does it take up? Understand? So let's go ahead and develop a formula for that. I'm feeling better already. Sometimes I just have to get in here and start talking about math, and I feel better. When that stops happening, that's when I'll hang up my boots. When I no longer get excited about this stuff. Okay, so we're going to use an integral, obviously, right? We're going to add things up, but we got to figure out what we're going to add up. So let's imagine we take this curve, right? We started at A, ended at B, and we want to wrap it around to get that surface area. Now, what I'm going to do is exactly what I just did a second ago. I'm going to take a little tiny little section right here, and I'm going to zoom in on it, okay? When I zoom in on it, I get this piece again, right? Okay, so it's the same sort of concept. But instead of trying to figure out how long this is, right, what I need to do is I need to imagine what that piece would look like wrapped around. So if I wrap that around the x-axis, what shape do you get? Take this and wrap it around the x-axis. What is this thing you're looking at? What does it look like to you in your mind? How would you describe it to someone? Like a ring? Like a ring? Rubber band? Maybe something like that. It's going to be a little, like a tape, like a little piece of tape looped around. So this thing wrapped around, just that thing wrapped around, would look like this. Ignore this for a second. That's just to let you know I'm talking about that same piece we were talking about before. Okay. In fact, I think I'll get rid of it. So if I wrap this thing around the x-axis, just the red, I get this thing that looks like this. Right? That's not solid. Do not confuse that with this. Right? It's not a cylinder on its side, right? I could put my arm through the center of this thing, right? And so I would like to know the area of that thing. The area. So I think what we could do is something we did before. Let's just take some scissors and cut it right there. All right? Let's cut this ring like that, and let's lay it flat. And when I lay it flat, now it's going to look like a piece of tape, kind of, right? Now, I intentionally did not put the edges on there. And that's because I know a lot of you want the width of this to be dx, right? You want the width of this to be dx. But it came from the red, right? So we are going to use the red as the length of this side right here. This is the red. And so if I want to know the area, that's pretty close to being a rectangle. Would you agree? Pretty close. And again, this is where, when you do a limit, the error will go away. How wide is this now? It's not dx. What is it? Well, it's the formula we just used for arc length, isn't it? It's that red is the arc length, which we already derived the entire formula for. This is just the square root of 1 plus the derivative of the function squared dx, right? That's how wide this little strip is. And then you need how tall it is. Okay, so how tall is this? We also did this before. If this was it, right, initially, now of course it's really thin, but this is all I've got, okay? If I took my belt off, right, this would look like my belt, and I'd lay my belt out, then my belt would be, what, how long would it be? It would be the circumference of this, right? And we just proved circumference is 2 pi r. So we know that this is 2 pi r. 2 pi, I'll use lowercase r, 2 pi r, but what's r? R is the distance from the center to here, right? Which for us is what? That's just the function, isn't it? We're rotating around the x-axis, so this would be our function's value would be r. So this becomes not that, but 2 pi times f of x. So this is how wide it is. This is how tall it is. And so the area of that is this times this, right? The area of that one little piece. So this thing's area is how tall it is, 2 pi times f of x, times how wide it is, which is the arc length, square root of 1 plus the derivative of f squared dx. And that gives us the area of 1. One little piece, right? We want to add them all up. Bring the integral in, right? Again, this is like that formula that we found for the cross sections, or in the previous for the little arc lengths. We find a formula for what we're trying to add up, and then we use the integral to add them up. So now finally the formula, and this is in your sheet, right? It's there on your handout that I gave to you. This is it right here. X-axis rotations. If y is a function of x on some interval ab and it's rotated around the x-axis, there's our formula. So it's the integral. I'm going to put A, total area. Remember, that's the area of just that one piece, right? The total area will be the integral from A to B, and then this, right, inside the integral. But 2 pi is a constant, so just pull that constant out. And then you have f of x square root of 1 plus, you've got it there, right? So f prime of x, that quantity squared dx. So do you see that this formula is almost the same as the arc length formula? It's almost the same. There's one additional thing. The additional thing that we have is that we have to add this f of x out to the front of it, which wasn't there with arc length, and we have to put a 2 pi. If we do that, we're in business. Okay. Shall we do an example? Yes?
Will it always be f of x, or will it be the distance from the axis of rotation?
Great question. So the question is, will it always be f of x, or will it be the distance from the axis of rotation to the curve? It will always be the distance from the axis of rotation to the curve, but I'm not going to ask you that. We are only going to rotate around the x-axis. That's it for these. For surface areas, we're only going around the x-axis. The book only goes around the x-axis. Well, they go around the y-axis too, but they don't move the lines up or down or below. You know what I mean? Like on the volumes. So on your test, the volume problems, yes, your axis of rotation could be below or above or to the side, right? But for surface areas and arc lengths, I promise your axis of rotation will be the x-axis. That's it. All right? All right, so now, let's do an example. Hey, let's try that sine problem again. The one that didn't work for arc length, right? And we had to go to the computer. Do you think we can find the surface area? What sounds like a harder problem? If someone were to say, hey, take the sine curve, figure out how long it is, or figure out the area if you wrap around the x-axis. Which one sounds more complicated? The area sounds more complicated, right? Let's see. Let's see. I'm pretty sure it's going to work. Because don't we already know from that example, do y'all remember what this was with the sine example? It was 1 plus cosine squared, right? But what are we going to have outside the integral now? Sine. So I have cosine here and sine there. And that's sine's the derivative of cosine off by a constant. Basic U sub should work. Okay, but let's do it, all right? On the test, will you have to memorize all the... I think we talked about this, didn't we? What did I say last time? Well, didn't... You asked, right? Yeah. I don't know. I might feel especially nice on this test. Who knows? I might let you all use that sheet. Here's the problem with me. You know, I personally would let you use all the formulas, you know? But the problem is I'm not setting you up for success that way. I hate that phrase. But eventually, at some point, you're going to get into classes where you're not going to have formulas. Like, you have to memorize stuff. Like, when I was in Cal 2, I had to memorize this. When we get to chapter 8, and we have all these different tests that we do, I had to memorize the tests, too. Like, you'll see once we get there. Here, I let you have the tests. Like, I give them to you. But I don't know. I mean, it's not... I understand that in the real world, right, you're never, like, stuck without any resources, right? You can always go to formulas. But to help you like get used to that stress of having to memorize something, I feel like I need to push you a little bit to memorize, right? Maybe not everything, but if I tell you, hey, you have to know the volume and area formulas, like then you have to know them, right? Let me think more about it. All right, what am I doing? Bringing up the picture again? Yeah, that one right there. All right, how do I say this? I want to find the area of surface, or surface area, if y equals sine x on the interval 0 to 2 pi is rotated about the x-axis. Does anybody think we're going to get 0 as an answer? If I asked you for the area, right? If you did the integral from 0 to 2 pi, right? If you did this, I did it in class. I already showed this to you. Right? If I asked you to do this, your answer would be 0. And that's because we learned that the area above counts as plus and the area below is minus, so they cancel each other off, right? What do y'all think? Do you think we're going to get a 0 surface area? You think? Maybe? No? I don't know. I mean, there's only one way to find out, right? To do it. Okay, so find the area of the surface if y equals sine of x on the interval 0 to 2 pi is rotated about the x-axis. So I'm taking that curve right here, 0 to 2 pi like that. I'm rotating it around the x-axis. And so really, I just automatically go straight to the formula. 2 pi integral, here I can say 0 to 2 pi, right? What comes next? Sine of x, right? F of x, sine of x. And then square root of, and the reason I'm going straight to this because we already did this, right? Okay, so I mean, you would have to do scratch work if this was a brand new problem. 1 plus cosine x, or cosine squared x, dx. All right. Can we do that integral? So now I'm going to step over here and do some scratch work. And I'm going to still do it in black because that's all I've got today. All right, so here's my scratch work. My scratch work is I'm trying to figure out what this integral is. I don't need the 2 pi. I'll leave the 2 pi out there. Just remember we have a 2 pi over there. I'm doing the indefinite integral over here. Right, so no limits of integration. I need to see if I can find the antiderivative. So I see a basic u sub. I see a basic u sub, right? U is cosine. Why not sine? Because the derivative of sine is cosine and it's underneath the roots trapped, right? We don't do it that way. But if I let u be cosine, the derivative of it is negative sine. It's out there, right? It's off by a constant. So du would be negative sine x dx. I don't have negative sine x, I have positive sine x, so I just multiply both sides by negative. And now I can try and rewrite the integral. So I'm going to replace cosine x, right? Not the square, just the cosine with u. And I'm going to replace the sine x dx with negative du. Okay, integral. Let me do the square root part. Square root of 1 plus what? U squared. 1 plus u squared. And then the sine x dx became negative du. Let's take that negative outside the integral, du out here. Everyone good? Okay, how would you do that? Trig sub. Or is there a formula? Pretty sure it's here. 21? Look at number 21. You know what? Can I borrow it real quick? Formula 21. Formula 21. Here, for Formula 21, the a for us is 1. Do y'all see that? A squared plus u squared. So a is 1. Let me write this down. According to formula number 21, I have the negative that was sitting out here, negative. And then I have u over 2 square root of 1 plus u squared plus a squared, a was 1 for us, so 1 over 2, and then natural log of absolute value of u plus the square root of a squared plus u squared, so 1 plus u squared. They don't have the absolute value on there. That's okay. Plus c. Okay, that is formula 21. Thank you. That is formula 21 with a being 1. All right, now what is u for us? Cosine. Right? Cosine. So let me come back. I'm ready to come back over here. They're ready to continue over here now? Okay, this should be equal to the 2 pi we had, right? The 2 pi. Hold on, I have a typo. This is a plus in the formula, right? That's a minus? The minus distributes. So let's put all that in brackets. Okay, that would have been a mistake. Okay, so let's do this. Let's take the minus, let's put it with the 2 pi. Minus 2 pi. Okay, bracket. Right, u is cosine, right? So cosine x over 2, weird, square root of 1 plus cosine squared x plus 1/2 natural log of cosine x plus square root of 1 plus cosine squared x. All of that, right? That's my antiderivative. All the u's replaced with cosine, but I'm now over here, so I'm evaluating this from 0 to 2 pi. Okay. What do y'all think? What are we going to get? What's the value of cosine at 2 pi? Cosine's the x-coordinate, right? 1. What's the value of cosine at 0? 1. Do y'all see that these would give you the exact same answers if you plug in 2 pi or 0? And so they're going to subtract and become 0. So it gives you the net surface area. It's a little weird, isn't it? So if I wanted to actually find the true surface area, how could I work around that problem? Go from 0 to pi, right? And then double the answer. And that's easy to fix right now. Can't I fix that here? Let's just scratch the 2. Scratch the 2. Doesn't change anything else except right here, right? And now we plug in pi, and then we plug in 0, and we get our 2 answers, right? I'm not going to do it because, I'm going to need a calculator because when you do the natural log part, you're going to need the calculator. So why don't I just do this? I'm going to go to Wolfram. This is just to show you that we can actually do this one. Like we can calculate this. Oh, can I go up here? Oh, I should just be able to edit. Oh man, that's awesome. I can just put in sine x right in the front. Let's see if it can give us a closed form answer. It should get this antiderivative. I forgot the 2 pi. Oh well. All right, you see their answer? You see their answer? Is that our answer? This is when I know that my internet students are cheating. This is exactly when I know they're cheating, when they give me that answer. Because this is what a human does, right? That's what a human does. That's what a computer did. So is this part, remember the cosine over there is u, right? Do y'all see that we have the first part? That's cosine over 2, negative 1/2. That's the very first thing. See how it says negative 1/2 cosine x? And then square root of 1 plus cosine squared x. We have that first part. This part right here is the part that's different. They distributed the negative. They used the fact that this is the definition of hyperbolic inverse, sine hyperbolic inverse. which most humans are not going to remember that that's what sine hyperbolic inverse is, right? So, okay. I want to leave this alone and move on. Can I do that? Can we trust we can just type it in and get the numerical answer? Yeah, okay. All right, I have one more thing. See, I'm going to go over the time. I thought it was only going to be 40 minutes, but I want to finish one more thing, all right? And that is, we've already proven in this class, this will be the last one we prove, so don't get too sad. This is the end. We took a circle, right? A circle of radius r. What have we proven about it? We've proven, well, the area is pi r squared, right? Got it. We just proved that the circumference was 2 pi r using the arc length formula. And then when we look at a ball, right, a sphere, we were able to prove that the volume of this was 4/3 pi r cubed, right? We've proven all three of those in this class. What's left? Surface area of this ball. What's the area of this? Well, what could we do? What could we do? How could we get the area of this sphere? Yeah, let's take this top corner again, right? Let's take that top corner. Let's draw it in red. Let's take this top piece right here, which we've already discussed. This is just square root of r squared minus x squared. It goes from 0 to capital R, right? We've been down this road many times now. And let's wrap this around the x-axis and find the surface area, right? And then double that answer, and that would give us the total. Right? So a lot of this we've already done, right? Go back and look just at what we just did. If we're going to do area, can somebody tell me what the integral was? When we were doing arc length of this red piece, we set up this integral. It went integral from 0 to r, square root. It was 1 plus x over r squared minus x squared dx. Remember when we were at that stage right there? And then we cleaned it. Oh, yeah, x squared. Yes, thank you. And then we cleaned that up a little bit. And this turned out to be integral 0 to r. It was capital R over square root of r squared minus x squared dx, right? Remember when we got to that stage? Okay, this piece right here, right? This piece right here is going to be exactly the same in that new integral we have. The only additional thing is what? In front, we're going to have to stick what? F of x, and then we're going to have to put 2 pi out here, right? So we're going to have to put f of x here and 2 pi out here. Yeah? Okay, let's do it. The area will be, okay, the 2 pi. Integral 0 to capital R. What was f of x? Well, it's that function, right? Root, square root, root r squared minus x squared. Yes, you were right. That's f of x times this. Do y'all see what's going to happen? It's freaking unbelievably nice. Yeah, those square roots cancel, don't they? Completely go away. And so you're integrating a constant. There's no technique of integration, really. I mean, you could even pull that constant completely out and be integrating 1 dx, right? Pull that, these cancel, pull the r out, 2 pi r, and then figure out what this is. So this is 2 pi capital R x, right? The antiderivative of 1 is x, evaluated from 0 to capital R. What happens when you plug in r for x? You get r squared, and you plug in 0, it goes away. So this is just 2 pi capital R squared. That's your answer. That's half of it, right? Double it. What do you get? 4 pi r squared. Now, if you look at your formula sheets, the very first sheet on your formula sheets, the very first reference page 1, very, very front, should have the pictures of the, does it? Yeah, look at it has the picture of a circle and has a picture of a sphere, right? Has those two formulas, has those two formulas. And we've proven them all now. All right, we're done. Chapter 7. The homework for here is same thing. You're just going to have to go play with the problems, see what kind of... I'm not done with Chapter 7. Shit. We may not get into... We'll at least start Chapter 8. There's one more thing I want to show you. I'm sorry. I can't not do it. But the homework for this. As far as homework, you have everything you need now to try your homework. All right? This is really just because I have to show this to you. It's a famous paradox. So there's an angel, and I think it's in Christianity or Catholicism. There's an angel named Gabriel, okay? And this paradox is known as Gabriel's horn. And I guess Gabriel played a horn? I don't know anything about it, okay? Just this angel played a horn. And so this is called Gabriel's horn. I don't know who made up the name, just telling you what it is, all right? So this is Gabriel's horn, and it's a classic mathematical paradox. So here it is. What I want you to do is take a look at this. Y equals f of x equals 1 over x. And I want you to look at it on the interval 1 to infinity. We all know what that looks like? We're only looking from 1 to infinity. So if you were to graph this, what's the value of that function at 1? 1. So at 1, you're at 1. And then as you go to the right, it should asymptotically approach 0, right? So it goes like this. But it never gets there, right? Got it? Now, wrap it around the x-axis. Wrap it around the x-axis. So when you wrap that around the x-axis, you get Gabriel's horn. Where's Gabriel? Where's the angel playing this horn? Out at infinity, right? I don't make this shit up, okay? Like, do you see? It's like a funnel that goes down forever. Gets smaller and smaller as you go.